Take it away, guys.
Thank you. It's a pleasure to be here at the StanCon. And I'm not alone. I'm here with my colleague Zeno, and we are going to talk about matrix completion for applications in the chemical industry. And for over about 6 years now, we've been developing matrix completion methods with the help of Stan. And today we're going to show you some of the examples. So to start, let's talk about the chemical industry. In the chemical industry, we have a variety of raw materials. And then we process them, and they get turned into products that we all know from our everyday life. So, for example, polymers or pharmaceuticals. And the process steps to get there can be divided into two categories, basically. So one being chemical transformations. These are the reactions that take place to create the product that we need. But unfortunately, we usually don't end up with pure products right away. Usually we have mixtures with sometimes hundreds of different chemical components. So we need a lot of separation and purification steps. And for all of these steps, we need to know how the mixtures that we are dealing with behave. That means we need to know the mixture properties. For example, the solubility of our product. So how can we get these properties? One way would be to do experiments, right? But this usually don't work. The reason is simple, because we have around 120,000 technically relevant pure chemical components. And as I said, we're not interested in pure components, we're interested in mixtures. And we have already 7 billion possible two-component mixtures, so binary mixtures. And if we go to ternary and multi-component mixtures, this is just a combinatorial explosion, and we cannot measure everything. We need good prediction methods. But here's one good thing. If we know how binary mixtures behave, we can extrapolate to multi-component mixtures using physical theory. That is why binary mixtures are so important, and that's why we are going to focus on binary mixtures in the following. Okay, now to give you an example, let's talk about gas solubility. We all know not to let carbon dioxide into the atmosphere, right? So what can we do if we have a gas stream that is rich in CO2? We can use a solvent, that is a liquid, that is used to take up the CO2 from the gas stream, so we can let the CO2 lean gas into the atmosphere. But gas solubility is not only important in the chemical industry, it's also important, for example, for fish to know how much oxygen can be dissolved in a body of water. And now the property that describes this gas solubility is called the Henry's law constant. And now what we did is we have taken all Henry's law constants at 25 degrees Celsius from the Dortmund data bank. This is the largest data bank on thermophysical properties in the world. And we can arrange those data points in a matrix, which is shown here, where the rows correspond to the gases, so the solutes, and the columns correspond to the liquids, that is the solvents. And as you can see, this matrix is not complete. We have a lot of gaps, which is indicated by the black area. In fact, only about 11% of this matrix has been measured. And our goal is to complete this matrix. This is a matrix completion problem, which is well known in machine learning, and especially in recommender systems. And that's why I'm going to explain the idea how we can complete this matrix with the example of Netflix. So Netflix also has a matrix, which is sparse. Here we have the rows corresponding to the users and the columns corresponding to the movies. And of course, not every user has seen every movie. But we want to fill the matrix so we can give good recommendations. What can we do? We can learn user and movie-specific features. So similar users will have similar features. And after learning those features, we can predict every user-movie interaction. That means we can fill the entire matrix of movie ratings. And now we have transferred this idea to thermodynamics. Here we have a matrix. This time it contains mixture property data. And the rows and columns correspond to the solutes and solvents. Again, we are learning solute and solvent-specific features. we can do this, for example, by simple matrix factorization. And after learning those features, we can then make predictions for every solute-solvent combination, in our case, every gas solubility. And this is what we call a matrix completion method. And we've done this using a probabilistic approach. So for every feature, we used a normal prior, and we're using usually a Cauchy likelihood. And to find the posterior, we're using Stan's variational inference. Now let's have a look at the results. These are shown here. I'm going to show two plots. One is a parity plot. Here we can see our predictions. Data that we overestimate are in this area. Data that we underestimate is in this area. And accurate predictions are on the diagonal. And we can also illustrate the results using a histogram, where the number of data points is plotted against the specific accuracy. So data that we overestimate is here, what we underestimate is here. And accurate predictions are in the bin in the middle. Now, to really assess the performance of our method, we need to compare it to a benchmark. In our case, we're using a physical benchmark, the so-called PSRK model. I'm not going into detail here, but it's the most accurate model for predicting Henry's law constants. And this is shown here in red. So we cannot directly see in the parity plot which model performs best, but we can see here in the histogram that we predict way more data points very accurately compared to our physical benchmark. And this is already pretty astonishing, because we're only using a purely data-driven approach. But these two methods, the data-driven MCM and the physical PSRK, don't have to compete with each other. We want to combine them in a hybrid approach. And how can we do this? One way is a two-step approach. So we start with the pre-training step. We train our MCM using predictions of the physical model to generate an informative prior for the next training step. And to illustrate this, here's a density function of one feature. And we start with a standard normal distribution. And after the pre-training step, this feature is updated. Then we train on the experimental data. And now we use the informative prior from the pre-training step. The features are updated again. And we can make predictions for the entire matrix of Henry's law constants. Now let's compare our hybrid approach with our data-driven approach from before. This is shown here. Here's the data-driven approach again in blue. And here's now our hybrid approach in gray. And we can see that we have still some improvements here in the histogram. And we can see in the parity plot that especially these large outliers are now way closer to the diagonal line. So that means our hybrid approach is more robust towards outliers. And this can be seen, for example, in the mean squared error. So for our hybrid approach, we can achieve a mean squared error that is less than half of what we get for the data-driven model. So that means we now have a model that has a large scope. It can predict every mixture in the matrix and is very accurately and robust in predicting gas solubilities. And with that, I'm going to hand over to Zeno, who is now showing you another important mixture property in the chemical industry and how we predict it.
Thank you, Nicholas. We'll now move on to a different thermodynamic system, aqueous electrolyte solutions. You've probably all heard the term electrolytes before. 2 days ago, we had our conference dinner where I might have had a little bit too much delicious Swedish beer and felt a little bit hungover the next day. Taking electrolytes is often recommended to get rid of this feeling quickly. But electrolytes don't just show up in hangover treatment, but also in many industrial applications, such as battery technology, water desalination, or wastewater treatment. What actually are electrolytes, though? To answer that question, let's take a look at one of the most basic, most common examples of an electrolyte that we all know from our everyday lives, table salt or sodium chloride. If this compound is added to a solvent, such as water, it will dissociate into two new components that carry a charge, namely, in the case of sodium chloride, a positively charged sodium cation and a negatively charged chloride anion. Now, to model such electrolyte systems for process modeling in the chemical industry, we need information on their so-called activity. Activity is one of the most fundamental mixture properties in thermodynamics, and it's basically an effective concentration that takes into account how much a component wants to react. And it governs things like solubility, for example. In the case of electrolytes, as the activity, we distinguish between the activity of the ion or the electrolyte gamma and the activity of the solvent, water in this case, phi. These two properties are connected. They're basically two sides of the same coin. Now, unfortunately, we don't always have experimental data available for every system, so we often need to rely on established thermodynamic models. And one such model is the Bromley model. I won't go into too much detail here, but the important thing to retain is that it allows us to calculate the activity coefficient of electrolyte, ion, or solvent as a function of concentration, and for this it uses a single electrolyte-specific adjustable parameter, BCA. So, for example, one parameter specifically for sodium chloride. This is also the limitation of this model, though. This BCA parameter must be fit individually for every single electrolyte based on experimental data. So let's take a look at what experimental data we have available. Because we're always dealing with pairs of cations and anions, we can organize the availability of data into such a matrix where the cations are represented by the different rows and the anions are represented by the different columns. Our BCA parameter depends not only on electrolyte but also on the solvent and temperature. So we're sticking with a single solvent, water, and a single temperature, 25 degrees Celsius, for now. Those matrix cells marked in blue are those where we have experimental data available, so we can use the Bromley model to fit our Bromley parameter too. But in all of this white area, we cannot do so because we don't have any experimental data available. That is, unless we consider this to be a matrix completion problem. We can solve it using a matrix completion method. How does this work? We start with our experimental activity coefficient data that we can get from a database. Here we have some data points for some electrolytes. And for those electrolytes, we can then calculate the Bromley parameter BCA and put it into such a sparse matrix. Using a Bayesian matrix completion method, as Nicholas has already shown you, we can complete this matrix so that we now have a predicted Bromley parameter for every pair of every cation and every anion in our matrix. We can use Bromley's model to then calculate the activity coefficient as a function of concentration for any of those electrolytes. We train this model end-to-end on the experimental data. All of this is done in Stan, and we call this model the Bromley MCM, which we've evaluated using a leave-one-out cross-validation. Now here you can see some of our predicted activity coefficients for some exemplary electrolytes. For the electrolyte activity coefficient on the top, the water activity coefficient on the bottom, as a function of concentration on the x-axis with experimental data marked by the hollow circles. The black line is the prediction of our Bromley MCM. And the blue and orange lines are basically the current gold standard models for the prediction of activities of unstudied electrolytes. And as you can see, our Bromley MCM manages to very accurately predict the activity coefficient across the concentration, and also manages to outperform these previously established gold standard models. Now, we've so far only looked at a single temperature, 25 degrees Celsius, but in practice, industrial processes are rarely run at a single and constant temperature. So capturing temperature dependence is very important. And we can luckily do this by slightly adjusting our model. We can take all of these single temperature data and essentially stack it in the shape of a tensor using temperature as a third tensor dimension. We now have a Bromley parameter tensor that is very sparse that we can complete using a tensor completion method. For this, we use Tucker decomposition and generate predicted Bromley parameters for all of those electrolytes at any of those temperatures, and do the same for the activity coefficients. And we call this model, again, everything implemented in Stan, and we call this model the Bromley TCM. Now, how well does this model perform? We can already compare it to our Bromley MCM that you've seen before at 25 degrees Celsius, which was also the only temperature that we could have used the MCM at before. We can see that we maintain the prediction accuracy of the Bromley MCM. We're even a little bit better. But we now also generate accurate and thermodynamically consistent predictions across a very large temperature range. And this is really fantastic because we previously had no model for predicting the activity coefficients of unstudied electrolytes across such a large temperature range and also such a large chemical space. Now, allow me to summarize what we've shown you. We've developed matrix completion methods for the prediction of many different thermodynamic mixture properties, including gas solubilities and activity coefficients in electrolyte solutions. But these have just been 2 examples, and we've actually already applied Bayesian matrix completion methods to many more thermodynamic properties in the past. For this purpose, we've used hybrid models that combine a physical model with a machine learning model and found higher prediction accuracies and also typically a broader scope than was possible with those established models. And all of this has been made possible thanks to Stan. Thank you for your attention. We're happy to answer any questions you might have.
Hey, great. Have we got any questions in the audience? Oh, there we go. They all appeared at the same time, right at the back. Do you want to run it up for me? Is that okay? Well, that's the second row from the back. Oh, or down the front. Fingers pointing in all directions. You have one at the front. Let's start here. Thank you.
So for the Netflix problem for completing the matrix, it's sort of arbitrary where the users and movies go, because there's not like an ordering of users and an ordering of movies. Is there structure within this electrolyte data or the kind of data sets that you're accessing where you have some structure within the matrix itself rather than just treating them as kind of independent categories, or does that latent factor analysis that you're kind of doing lead you to discover that kind of structure?
Usually we do, actually, as you said, the other way around. Later we find structure in the features that we learn, and we can use the features to cluster then the components. Then we find things that we know from chemistry already, that we can find clusters that we see in the data. But it depends really on the mixture properties. We have some properties, for example, here the gas solubilities. There you can see structure because if you have a smaller molecule, it's usually less likely to be good soluble in general. But some properties are purely mixture properties, so you cannot see anything from the individual component. Only in the mixture it can behave with some other components completely differently than with some others. Yeah.
Thanks.
Yeah.
Do we have any other questions? Right at the back. Far right for you. Good throw.
Yeah, thanks. I'll blame it on after-lunch slowness, but it wasn't entirely clear to me how you evaluated it. I mean, the whole point is to fill in this matrix, right? Mm-hmm. But how do you know, in your evaluation, how do you know how far off from the true values you are, because you don't have the true values? So that wasn't entirely clear to me.
Yeah, what we always did was cross-validation. Usually in these cases, leave one out cross-validation. So each data point was left out once and then predicted and then compare the experimental data with the true predictions. So these were all true predictions that we've shown here.
Okay, so the evaluation was only on the values that where you knew the true values, not the black slots.
Yeah.
Okay, I see. Okay, thank you.
Let's thank our speakers once again, but we've got to move on to the next presentation.
Okay.
Thank you.